Hello all. All right, in this video, we're going to take a look at some very, very big conceptual issues. These are themes in artificial intelligence. Oftentimes, there are multiple subfields that are working on these themes, and some of them are just gigantic, and some are less so. So we'll take a look, and I'm going to suggest some of the big issues within each theme, and also provide some starting resources if you wanted to investigate them more. So, big themes in artificial intelligence. So, we're going to start with the idea we've already talked about that artificial intelligence is often defined by those things that we cannot yet get computers to do. But that crosses a really wide gamut. And you'll see that with most of these themes, even where we've made progress, we haven't made all of the progress that we would want. And there's still plenty more research and interesting experimentation to do. All right, so here are our important themes. We're going to talk about each of these in more detail. Intelligent agents, that has to do, as I said before, with that idea that an agent exists within an environment and it interacts with that environment through some sort of sensors that give it input and some sort of actions it can take. Reasoning is a big issue. Means like being able to actually explain why decisions are made and making decisions on maybe a rational basis. Knowledge has to do with information that an AI system needs to have. How do we represent knowledge? How does knowledge exist in an AI agent? And how can it use that knowledge in order to do the things it wants to do? Learning is a very broad term and it's a very weighted term, so we want to be careful how we use it. This encompasses machine learning, but traditional machine learning is at times almost not even AI-like. So there are other kinds of learning that maybe fit our idea of an intelligent agent better. We'll talk about some variations there. Communication is another one. This is primarily natural language processing. So this is dealing with text, dealing with speech, understanding and producing it. This is where these chatbots have had such a huge leap forward, but there's still a lot of work to be done. And there's increasing work done on not just speech and text as modalities, but also body language, movements, gestures, those kinds of things as additional ideas. And then there's this notion of embodiment. And this is really where robotics comes in. The idea of embodiment is that you have an agent that actually exists in the real world. It has sensors that sense the real world and it interacts with it. And that's kind of an interesting and important idea. So this slide also raises the question of what is AI complete? So that AI complete as a term basically means which of these, to solve it, we also need to solve the artificial general intelligence problem. If something can't really be completely solved unless we've got artificial general intelligence, then we say that it is AI complete. Yeah, and so the question is just how many of these can actually be fully solved if we don't have artificial general intelligence. All right, just now we're going to take a look at each of these in different themes in a little more detail. We've talked already a little bit about intelligent agents. And so this is somewhat of a repetition. They exist in a real or a simulated environment. They sense that environment, some kind of sensors or some way of getting input, and they can have an impact on that environment. We use the term actuator as a fancy term that means anything that the agent can do that will change something about the environment. That could include a speaker, just to make noises. It could include motors that let it move things. All kinds of different actuators are possible. This also shows the sense, decide, act loop, which intelligent agents engage in. They sense the world, they decide how to respond, they take actions, and it cycles again. Different agents go through this cycle faster or slower. Some go through it multiple times a second. Some, maybe it's more like playing a chess match where there might be minutes in between different rounds of this loop. And agents can differ greatly in how complex their decision making is. We're going to start looking at reflex agents that have very, very simple decision making, but you can go up to agents that reason about their own goals and the utility of their actions and all of those kinds of things, beliefs about others and all that. So there's a wide range of different kinds of agents out there. So I have a couple of resources here to start you off, and you will have a copy of these slides so that you can actually use these links. We will look at simple reflex agents in class, and then we'll gradually build more complex agents as we go forward and look at additional topics. So a couple of particular kinds of agent work that's out there. Agents in video games. So this would be both non-player characters or AI that is used to control aspects of the game, but also designing AI agents that play games and see if what it takes to have success in various games. So I have a couple of links here that you can look at. There's lots of other games besides these. I included Super Mario because I found that link, and there are lots and lots of different systems for building bots in Minecraft, and that I included a link to one of those. Similarly, AI agents have been used a lot in movies for CGI purposes. Oftentimes, background crowds are now implemented as agents, each of whom is maybe a reflex agent. It has some goals, it has some things it wants to do, and it's interacting with its environment in a way that makes those background characters, non-player characters, more interesting in how they behave. There's also an area of research called multi-agent systems. This is a really interesting area because it's all about how do agents interact with each other and what emerges when you have multiple agents who are either competing or cooperating together to solve a problem. So I encourage you to look more into any of those if you find them interesting. The second big theme was reasoning. This is actually still a really big issue because right now, even with chatbots that can do so many things, they can't explain their reasoning very effectively. And so there's been a lot of work just in the last year or two on trying to develop systems that can explain their reasoning. And there's also a move within artificial intelligence of building explainable AI. So focusing on AI methods that are more easy to have them explain what they do. So reasoning is really about that, the sort of laying out of a reasonable, rational explanation or making decisions on a rational basis. This includes things like proof systems, things that can do automated proofs, planning systems. We are going to look at one simple example, which is state space search, where it searches through a space of possibilities to find a solution to a problem. So this is an important core area. It's been around for a really long time within artificial intelligence. It doesn't get as much attention these days because machine learning has been so dominant for some time, but there are really good reasons why we like systems that can actually make rational decisions that we can understand, and they can explain their rationale to us. So here are a few reasoning resources. There's a little bit in our textbook about this. I also have a couple of nice pages about automatic theorem proving, and one that's sort of a history of expert systems. These were systems that are kind of old AI, but they are still useful in places where you really absolutely have to have that explanation. There's also a lot of current work on decision support systems. So these are systems that are meant to assist humans in making decisions and tracking what they're doing. So there's been a lot of research within the medical community and then more recently, just more broadly, AI-based decision support systems that you could have in industry that will help you make sure you don't miss something, that you haven't skipped any steps, that you're not overlooking some factors. They're really interesting to investigate. I also have some reasoning resources focused on planning. Here I included game AI because among the more complicated planning systems are systems within video games that control the game. And they try to make sure that the game is challenging for the user, but not too challenging for the user. So there are a number of AI-driven games where they adapt to how well the user is picking up the game. And so game AI is a place where planning happens a lot in a variety of contexts. That's one, and there are others. And there's also planning within multi-agent systems, which I thought was an interesting way to go about this. All right, the next big theme is knowledge representation. So we know that you can collect data about the world when you want to turn that into information, that means you somehow organize it. Somehow they can then transition into knowledge, which is a more permanent status, and where that information then connects to lots of other pieces of information that you might have. So we all have memories. We remember things. Our sense of how our memories work, our intuitions about how memories work are not very good. But we want AI systems that have memories too, that can remember their experiences, that can learn from them, that can remember things they've been told, that have object permanence. So the question then becomes, how do we do that? How do we build that information? And how far do you go with it? How much information does the AI system actually need? So if you work with machine learning or you work with neural networks, that's kind of taken out of your hands. The system determines the knowledge it thinks it needs. It's up to you just to sort of determine capacity and to some extent how that information interacts with itself. But we really can't see how things are being represented. They're just great big matrices of numbers, and it's very, very hard to figure out what exactly a neural network has done. So there's also a lot of work on building knowledge representations more at a more symbolic level, rather than having it be something that's just stored in a bunch of different matrices. So here I have a couple of links to sources that are more about that side of things. So knowledge representation and reasoning is actually, Wikipedia has a lot of great pages, so I encourage you to look at Wikipedia. And then another document that's just what is knowledge representation in AI. Those are good places to get a start if you're kind of curious about those approaches. All right, next is learning. I phrased it here as machine learning. But a lot of what, some of what we do that we call machine learning is really more data science than it is artificial intelligence. And that's absolutely fine. They're great tools for data science. But there's also, from an AI perspective, we want it to somehow connect to agents, to these AI agents. And a lot of machine learning work that's more like data science doesn't connect very well to this notion of an AI agent. There's no agent that's using the data. It's humans who end up using the data. So I'm going to encourage us to look beyond just straightforward machine learning and also think about the contexts where this makes sense as something for an AI agent. All right, so fundamentally, machine learning systems are statistical pattern finders. They look for patterns in data, they build a model that encapsulates the patterns that they've found, and they use that model to solve whatever task they have been set. They have extremely successful in recent years. It's really been the last 10 years, machine learning systems have been widely used. And of course, since the chatbots have come out and these large language models, that's a big jump forward in the kinds of models that we can work with and what their capabilities are. Your typical machine learning system its learning is done offline. That means while it's actually active and in use, it's not necessarily learning anything new. What it's doing is we go out and collect the data, we organize it, we pass it through this machine learning algorithm, and we get a model. And then we take that model and go and put it in use somewhere. And that model just sits there with the knowledge that it's already gained. With many of these things like large language models, they may be collecting additional data, but then there has to be some sort of offline retraining that's happening to make sure that the system is learning what it needs to learn. And classification or categorization tasks are like the most baseline of these. There are other tasks as well. In particular, large language models use word prediction. So given a partial piece of text to predict the next word, that is really what a lot of these chatbots have at their heart, although they have some additional tools, additional steps in more recent models. For AI tasks, we sometimes want something different. So we would like something that learns online. I have to say this is near and dear to my heart. I do a lot of the first kind of machine learning, but I'm also really interested in the second kind. Learning online means that the agent is engaged in a task. It gets feedback in a natural way from its environment, and it needs to learn from that. A critical approach there is reinforcement learning. There are others, but it may lead to something that learns in what feels like a more natural way than your typical machine learning approach. We are going to talk about a bunch of different machine learning tools, algorithms, methods in class, decision trees and k-nearest neighbors, and artificial neural networks. Those are kind of traditional machine learning. We will also look at deep learning, which is newer and has lots of variations. We will look at reinforcement learning, and we'll kind of look at Bayesian learning. So there's some machine learning algorithms that produce Bayesian networks. So we're going to look at Bayesian networks. We might look, if we have time, we'll look at the machine learning algorithms that generate them as well. There are lots of other, hundreds of other kinds of models, lots of other kinds of problems like regression, clustering, association learning. There's just a lot out there that could happen. We're not looking at all of it because you need to take a whole machine learning course if you want to learn a lot more. So much of our book is focused on machine learning because it's such a key part of modern artificial intelligence. And I give you here a couple of guides to reinforcement learning and a nice tour of machine learning algorithms that I thought was just kind of a nice, less technical look in a short term at a lot of different machine learning tools. Oop, I have a typo here. An NLP. Communication was our next big theme. Most of the work in AI has been around natural language processing because language is so critical to us as human beings. That's moving into other arenas, including looking at, say, ASL, or just how humans use gestures and body language to communicate. There's been work in vocal tones, like how we pitch our voices and vocal and the rhythms of speech that also carry meaning. That's often very culturally specific meanings. So we've moved beyond just plain natural language processing, but it's still a key component and a huge part of artificial intelligence. We're not actually going to do a unit on natural language processing, in part because it's just so big, and in part because it overlaps in some ways with the things that we are going to do. So we'll do some machine learning. You can apply that to natural language processing if you like. So you can see this long laundry list of different possible tasks. Each one is complex in its own right and can be the focus of a project, a research project. So speech understanding, so that's taking speech and figuring out what is being said. Chat bots are obviously huge. Being able to understand text that is given to it and produce text. Understand, that's a weighted term, but at least having gotten some text, being able to respond in an appropriate way to it. I'll put it that way. That's what I mean by understanding. Information retrieval. Sorry about that. I had an issue with my audio volume there. Information retrieval is all about finding the right documents. So chatbots can do that because they have so much information, but they don't always do it right. And so one of the things that we have to worry about is exactly how that process works. And there are other techniques that people look at. Interactive fiction. So having non-player characters in games that actually can talk freely to you and have a perspective that they can put forth. And then producing text, producing speech, machine translation, being able to translate from one language to another. Each of those is a giant, giant subfield of its own. So speech processing, this is kind of at the bottom level. There is a lot of recent work applying these large language models to speech processing. So you put an audio signal in and you have it predict the words that are going to come out that match. But before that, there was a lot of work done with other statistical models, particularly hidden Markov models and others in that vein that could model the signal processing. They could model phonemes and lexemes and converting from signals into those and from those into words and so forth. So there's a lot of really interesting work been done in speech processing. These days, there is some interesting stuff happening around machine learning, large language model based work. So I gave you a couple of links to some interesting projects and papers and just a general speech recognition Wikipedia site, which is actually like many technical sites on Wikipedia. It's very good. So I encourage you to look into that a little bit if it's something that might interest you. Information retrieval, it's kind of in the middle. Text understanding is on here as well because sometimes that plays into it. We do a lot of statistical language modeling. Rather than using large language models, we might use a more simple statistical model if we think it might work for us. And there are things like query retrieval. PageRank is the famous classic algorithm that Google used. What they use nowadays is anyone's guess, but this is their first big successful one. And it's doing something different. It's not large language model. It's doing something different to come up with appropriate documents. This is actually really, there's some really interesting work being done right here locally. Thomson Reuters is a local company, and the Reuters side is a news organization, and they probably do some of this too. But the Thomson side of the company does systems for law firms, for lawyers, so that if you have a new case, you want to pull up relevant case law. They do a lot of natural language processing research on how they can do that. Given a description of a case, how can they determine relevant case law that they want to retrieve? So there's a lot of really interesting places where we really don't want to just throw this stuff into an LLM because it might make things up or give us things that aren't as good. So there's still work to be done here in making these systems function to the best. I have a couple of links here to projects and also just a general more information about natural language understanding. Machine translation is a really huge problem. Good translation is hard to impossible for humans. Not everything can be translated well. There's a great book called Le Tombeau de Moreau, which was written by Douglas Hofstadter, who's a big name in artificial intelligence. And he's talking about a very small, simple poem that he likes that was in French, and the many, many, many different ways you could translate that poem. So if you want to do on-the-fly machine translation, that's an even harder task. When you have simple documents like business documents that don't have a lot of innuendo or metaphor or subtext, those are more straightforward to translate. Things that are more metaphorical, fiction, poetry, where imagery and rhythm and word choice is more important, those become really difficult to translate well. There was some work, there's a lot of work with machine learning models and like these large language models for doing machine translation. It does do better than some other approaches. There was a lot of work done on developing sort of an interlingua, so some sort of internal representation that was language independent so that you could then translate in and out of it. I don't know how well that ever worked. Statistical methods for machine translation have generally worked more broadly well, but you run into those issues with them that sometimes they are inaccurate. And so they need human observation, human checking in order to ensure that they're not going wrong. I have a couple of nice documents, blogs and other things like that that I found that talk about modern machine translation, what's going on right now. And a lot of that has to do with using neural networks and the ways in which they're used. All right, this last one is also near and dear to my heart because I work in robotics. I like this first line here. It says, maybe a real intelligent agent must live in the real world. So there are those who argue, and I'm not quite sure this is true, but it's an appealing argument, who argue that you cannot have artificial general intelligence unless you have an agent that is embodied, that has a body, a form that exists in the real world and interacts with the real world. That without that, there's a whole category of knowledge that is closed to a virtual agent. They can't understand what it feels like when the sun is shining on your face in a cool morning. They don't understand what the texture of wood feels like. They can't possibly understand what it sounds like when you're approaching a waterfall. So there's a lot of that sort of tactile sensation of the real world that may be important for real intelligent agents. It's also hard to build agents that have a lot of self-generated goals, because if it's a virtual agent, it doesn't really need anything. It's kind of got goals that we impose on it. But we don't really have the same kind of issues. Whereas an intelligent agent in the real world might have needs like power, energy, rest, shade, keeping it in the right temperature range. There's just a whole other world that's out there when you talk about embodied agents. Robotics is a part of this. Artificial life is also, and animats are related to artificial life. They're sort of virtual or artificial simulations of real animals. Uh, and there's just a whole lot of work that people also do on this idea of embodiment. I have a couple of links here. Mostly these are links to the topic of developmental robotics and social robotics. So these are places where people in robotics really grapple with these issues. So how could a robot learn like children learn, starting from nothing and experiencing the world and learning in that way? And social robotics is more about how do we have robots that interact with people in a natural way? How can they exist in their embodied form in a way that, and then we can encourage them to interact like a person would. All right, I'm going to stop there. This has been just a really quick, broad overview of a lot of different areas and themes that come up in artificial intelligence. They relate to a lot of the things that we care about ourselves, you know, communication and being in our body and the knowledge that we have and how we learn, all of those, and how we interact with our environment. All of those are aspects of our intelligence, and artificial intelligence as a field wants to reflect all of those. All right, going forward, we'll engage a little bit with some of these topics, and then we're going to jump in and dive a little deeper with a closer look at things like artificial life and reflex agents, and we'll build up from there.